Without further ado, I will go into the architectural presentation. And feel free to ask questions as it becomes a bit more complicated. If you have any questions or queries about the topics we're presenting.
First question we didn't get in the first presentation you did was where the name of the company came from.
Okay, so E8 storage stands for 10 to the power of 8. That's E8. That's 100 million IOPS, which is what we can get today from a cluster of E8. And also E7 was already taken.
So go big.
We appreciate the honesty.
All right, so I'm going back to the first slide we presented about the challenge of what we call the Gen 1 all-flash arrays, which is typically all the all-flash arrays in the market today that constrain the bandwidth and the throughput and impact the latency on the way from the customer servers to the SSDs. And it is the two controllers, or in some cases even just one controller, that have become the bottleneck, especially as SSDs have become faster. Especially with NVMe drives, this problem has really been exacerbated. NVMe drives have 10 times the bandwidth and IOPS of SAS drives, so this has become 10 times worse. So how can you solve this very challenge? The first thing that comes to mind is a scale-up solution. Make those controllers bigger, beefier, stronger. If today such a controller is a 2-socket Intel server, use a 4-socket Intel server, use an 8-socket Intel server. If today the CPUs are 14 cores, use 28 cores. Maybe even design your own custom hardware to solve this very problem. All of this are indicative of a scale-up problem because at the end of the day, it will still be a dual controller. And I think this is pretty much the picture of what the SSD did. So the problems with this approach are it's very hardware-centric. You're very much tied in to the hardware that you use. Even saying moving to a quad-socket server is not really practicable. Those are huge and expensive and power-hungry machines. So you're impacting cost and power and density. Obviously, this is a dead-end approach. The second approach is also one that's very common, which is scale out. If two controllers cannot do the work, just add more controllers. And the problem is that if two controllers are somewhat able to handle 24 SAS SSDs, and NVMe drives are 10 times faster, then for 24 NVMe drives, you need about 20 controllers. And we're literally seeing products in the market today that are attempting this approach. They're putting up maybe a dozen controllers to front a bunch of SSDs. This, again, makes it very complex. It costs a lot of power. It creates a problem of density. It is literally putting a blade server in front of your SSDs. It's very much a 2003 kind of approach that we think is a dead end as well. The approach that E8 has taken is quite literally thinking outside the box. And the idea is basically this. Given a fast enough network, and NVMe over Fabrics requires such a fast enough network anyway, what do you care if the all-flash array controller runs in part on the application servers themselves? And assuming you have a lot of such servers available to you, and we're seeing deployments of 40 servers, 70 servers, 100 servers, so there's no shortage of servers. If we take up one core on 128 servers, we got ourselves a 128 core distributed controller. That's the idea behind E8. And what does it solve? There's no bottleneck in this architecture when you think of it. When Bill showed the demo going to 10 million IOPS, what was the bottleneck that hit a limit of 10 million IOPS? It was quite literally the SSDs and the network. E8 is able to max out the properties of the hardware, both the networking and the SSDs. And we're using enclosures which have a balanced amount of networking ports to SSDs. Our 1U10 has got 400 gig ports, our 224 has got 800 gig ports. It is truly horizontally scalable. And again, Bill showed that in the demo very easily. One server was doing 1 million IOPS. You kick off another server, you're getting 2 million IOPS. And finally, to get to 10 million IOPS, we'd use something like 16 servers. But you can mix it out. You can have one core on 128 servers or two cores on 64 servers. it doesn't really matter to the architecture. It is completely horizontally scalable. Finally, in terms of cost and power and density, we have TCO calculations that show that it can reduce 70% of the cost of power compared to any kind of centralized solution that doesn't take this approach. And if you view the picture, and it's not a complete picture, but it truly is a controller-less architecture. There is no controller here. It is a distributed controller that's run on the application servers.
How do you do software updates in this architecture?
Software updates?
Yeah.
We have, through our management, through our GUI, we can deploy new RPMs to the stations and update them. Mm-hmm. We have a fully automated process for non-disruptive upgrade. Mm-hmm. So we have a non-disruptive upgrade of the software and the hardware that we use. Okay. It's been a key part of our value prop, because when you go into production, you really must be able to support such a thing, and it's a very tough feature.
Yeah, is it a rolling upgrade or is it simultaneous? Or?
In the controllers, it's a rolling upgrade. In the agents, it's simultaneous.
There's got to be some stun of the file systems while you're doing that, right?
Yes, there is file systems that attach to block devices have the ability to sustain a short period of I/O taking longer than typical. And this is fine. The local file systems and the applications riding on top of them can deal with such a transient period. So the question is, how do you connect NVMe SSDs to the network, or eventually to the servers that are accessing them? First option, and actually when we started the 8, it made the most sense in a way on paper, is a PCIe. NVMe SSDs are PCIe. The application servers obviously have PCIe. Why not go PCIe end-to-end? The answer is that PCIe is not really a fabric. It is not really a network. It is not switchable in the regular sense of the word. It is an extremely awkward piece of technology to handle in ranges that are longer than a single server. And we've seen products take this approach and fail. It makes more sense to go to Ethernet, and Ethernet speeds and feeds are fast enough to sustain NVMe over fabrics. But even then, there is a question, how do you attach to Ethernet? So again, a very possibly good approach would be, let's do a conversion from an SSD to Ethernet on the per SSD basis. So each SSD will connect directly to the Ethernet network. The problem with that, first of all, there's no such parts. But more than that, you're creating an explosion of ports. A given SSD would require about a 25 gig port without high availability. You'd need to double that if you want high availability. And now the SSD becomes a network element. So it needs to conform to all the networking rules and IP addresses and VLANs and whatever. It's a long list of things that a poor little SSD needs to do.
Well, it also means you can't allocate less than a full SSD to a server.
You can virtualize around it maybe, but we think it's a
you're
very...
building a volume manager into the interposer on the SSD, and costs go through the roof.
Yes. The approach we've taken is there needs to be a PCIe to Ethernet bridge / aggregator to chew up a bunch of SSDs and connect them to the network. That is the most practicable solution. That will be the cheapest, most energy efficient, and it will aggregate one of the 25 gig SSDs. An SSD is roughly 25 gig. It's not exact. But if we view it from Ethernet, that's the closest port rate. So from 25 gig SSDs, it will aggregate to 100 gig ports, which is what typically top-of-the-rack switch uplinks are. So that is what we think is the right way to connect SSDs to the network. Now, I will ask you this. Where can I find a PCIe to Ethernet bridge and aggregator?
Killa Systems, Kazon Network, Telray.
So good luck with that.
None of them shipping yet.
We have systems in production using a very simple PCIe to Ethernet aggregator and bridge, which is an x86 server. And an x86 server is a perfectly well-functioning, high-performance, ubiquitous, cheap, and abundant way to connect NVMe SSDs to an Ethernet network. All you need is an x86 server and a 100 gig NIC. Boom, you're done.
Well, you do need a little software in there, don't you?
So E8 Storage is the software provider exactly for this. We're not a hardware provider. We're not a hardware manufacturer. We use commodity components and commodity servers to achieve exactly this. By using an x86 server, it is an off-the-shelf component. It can easily aggregate, in our 1U10, it's 10 SSDs into 4 ports. In our 2U24, which you can see here on display, it is 24 SSDs into 8 ports. More than that, we use that footprint to host our metadata server, marked here in yellow, which is basically our software entity that needs to run somewhere. And a lot of virtual storage appliances have this problem of where the heck are they going to run? And we just solve that very simply by running it on our box. It constitutes part of the topology to get to the SSDs anyway. And this is where we serve our web GUI from. This is where we serve our RESTful CLI from. It's a very convenient thing to do to just run the MDS there. So that's, in a nutshell, the E8 topology.
Can you talk about the HA failover process, like we, because it was brought up before, how you go controller to controller failover?
Yeah, I think maybe it's even the next slide. So to drill down for a second, because it's part of the architectural explanation, in an HA enclosure, this is more or less what it looks like. It's 2 motherboards. In other words, we get the benefit of 2 such bridges or aggregators. Each motherboard can see all the drives by using dual-port and NVMe drives. Today, all major SSD vendors have dual-port NVMe drives. Sometimes I get asked, isn't that an expensive component? The answer is, it costs the same as a single-port drive because it's the same SKU from most SSD vendors. Only difference is, do you use it, do you connect it to 2 ports or not? The x86 motherboards serve as the translators from PCIe going to the SSDs to Ethernet going to the network. There is no single point of failure. Our chassis is designed with a passive midplane. You can literally go and check it out. There's nothing on the midplane other than wires, so it's a passive midplane. That is a critical part of a no single point of failure design. On the motherboards, there's a PCIe switch that fans out from the Intel complex to 24 SSDs because the single Intel CPU cannot handle 24 SSDs directly. The canisters are hot swappable, allowing for high availability and maintenance. We put 2 NICs on each motherboard, off-the-shelf NICs, supporting 100 gig Ethernet or 100 gig InfiniBand. We also have a battery backup unit, so we can sustain power failures. I'll get to that in a second, but we've already experienced 3 times power outages at customers' data centers. It is far more prevalent than what even we thought initially. The battery unit...
So are you using the system RAM as a write buffer?
Yes.
I forgot, or I didn't know it.
We're going to get to it in a second. It's a very important part of the design. The battery backup unit only holds up the motherboard, not the SSDs. The SSDs are the great power consumers of this platform. So having a battery for them is a lot of battery juice, whatever that's called. The SSDs we use are enterprise grade, so they have super caps, so they can sustain the power failure. And the battery units are only needed to power up the respective motherboards and flush the dirty memory to the local boot devices.
So you've got Ethernet and InfiniBand. What are you seeing in the field? Is it 50-50? Are most customers going into Ethernet or InfiniBand?
We have chosen to focus mostly on Ethernet, but the NICs we use are for Mellanox, so they're dual purpose. So it's a flashing of the firmware at factory if you want to go Ethernet or InfiniBand. But all of our deployments to date have been on Ethernet because of our choice.
Okay.
We are very much focused on Ethernet. We believe that's the ubiquitous data center fabric. But we also support InfiniBand, just by virtue of using that adapter.
And the network semantics for Rocky are modeled on InfiniBand, so the software looks very similar.
Yes, it's basically the same. So how does it work? We have 2 high availability schemes, and it's really a bit up to the customer to guide us. We prefer the D24. It's It's a stickier product. The first option, which is what we started out with, is actually having two distinct boxes that are not highly available, and you achieve redundancy by replicating between the two of them. The best way to do it is by having RAID 5 plus RAID 5. That would give you very good redundancy and resiliency. The replication at the server level can be done either by the application itself or by an LVM or something like that. It's a pretty good way to achieve.
Strictly speaking, you're not talking about replication, you're talking about the host writing twice.
Yes. The host writing twice. As you can see, the metadata server runs inside each box. Each box has got its own metadata server.
These are the single units.
No, it's 2 units.
I mean, these are the single, these aren't HA units. These are single.
No, it's a 1U10.
Right.
This could be any server. We often get asked, so why don't you just run it on any server? The main question is, who would give it support? If a customer installs the software and then complains that there is a network disconnect and we need to start reconfiguring his network, it's impossible to support. So we still prefer to sell our own S10 and deploy it in this manner. The other deployment model is with the HA box and dual port SSDs. In this case, each controller carries an MDS, so we have redundancy on the metadata servers. And we typically are first foot forward with RAID 6. That's what we always recommend. I think that the existing all-flash arrays have done a good job of educating the market that RAID 6 is important for SSDs. Nobody's arguing about the mathematics, justifying that or not anymore.
People are arguing with the mathematics. We're slapping them down.
Yeah, so to be honest, almost all of our deployments are with RAID 6 because that's what we recommend. The SSD performance is so high that doing RAID 6 doesn't really take away too much, and we feel that's a safer way to deploy.
No spares? Any spares or not?
The spare is virtual.
Right. Okay. Makes sense.
And the RAID calculations, they're done by the individual controller? That's my CPU.
I will show that in a second. The RAID calculations are done on the distributed all-flash array controller.
Okay.
I'll get to that in a second. Also, regarding it might be a bit too much info, but we usually stripe 16 plus 2 on 24 drives. So it's a virtual striping. It's not on a per disk basis.
Right.
16 plus 2?
On 24 drives. That's our typical.
Okay, but you don't have a write-in free space data layout underneath it, so that's a lot of read to modify write for small updates, isn't it?
So there is first of all, we support a bunch of RAID schemes, and some applications would favor a different RAID scheme. We have RAID 0, RAID 10, RAID 5, RAID 6, and in RAID 6 we can support any topology. We would recommend a power of 2 to achieve full stripe writes on a decent block size, but it could be 2 plus 2, 4 plus 2, 8 plus 2, or 16 plus 2.
16 plus 2 on a 24 drive leaves 6 drives untouched in a given write. Is that correct?
In a single full
A
stripe.
single write, right?
Yes. Yeah.
So then, what do you capture that 6 on the next write?
Yes.
I guess. Okay. So
Exactly.
So all right. So it's not a physical. Okay.
Yeah, it's chunklet style, not
Look
disk
that
style.
word.
Is there a better one for that? I mean, 3PAR made it up, but
Chunklet?
yeah.
That makes sense, yeah.
Yeah, we call it chunk. I didn't know 3PAR made it up. All right, so how is this done? So when we started the 8, we had a few challenges and requirements that we thought are very important to nail down. Unlike hyperconverged solutions, what we've shown you with a distributed controller, you could have asked, wait, how is that different from vSAN or any kind of hyperconverged solution? They run the controller on the host as well. And by the way, that's also the answer to, hey, how dare you run storage stuff on the controller? So when you think of it, all the hyperconverged guys have educated the market that that's a fair thing to do. So, Nutanix or vSAN or any of those guys, Scaleo. So people have become accommodated to it. But the hyperconverged architecture suffers. Its main Achilles heel is that the main Achilles heel of the hyperconverged architectures is that they're not really resilient to host failures. So maybe they can work around one host failure. Most of them completely crumble if there are two host failures. And God forbid what happens if you plug out the power.
Yeah, I've
So
had several hyper-converged solutions in the lab where if you lose power to the rack, you have to call support and have them rebuild it before it comes back up.
So I think that's one of the reasons that hyperconverged solutions are typically much smaller scale than people would have you believe, and are relegated to the kind of dev and test environments rather than
Well, they're not. It's not this level of mission critical application you put on that.
Yeah. So the key portion of the E8 architecture, which makes it really interesting and innovative, is that it's resilient to host failures. Now, we took the liberty of running stuff on the host, but we are not confident that the host will be forever up. So in essence, those agents or services we run on the application servers are stateless. We never store volatile metadata on those servers. So if you combine that with the need to support power loss, and you could argue about it, but in seriousness, we have experienced this already 3 times with 3 different customers. So if you need to support power loss, you actually need to be resilient to all hosts gone at the same time. That's a pretty tough thing to do. And that's one of the key areas where the E8 architecture really shines. The other thing, we wanted RAID 6. We actually have RAID 6 as part of our V1 already a year ago. That is what we have in production in the last year with all customers. We do support RAID 5 and RAID 0 and RAID 10, mostly to play with and show different performance levels. But to date, all customers opted to use RAID 6, which is safer than a RAID 10 or RAID 5, which have higher performance but are not as safe. Also, in terms, there's no read penalty. A lot of workloads today are read intensive, and they would prefer the high reliability. HA enclosure means no single point of failure. We thought that's a very important thing, and that's also part of our V1. And finally, network resiliency. Someone asked about it before, and multipathing. So we've seen a competitor say, oh, you can use our product with the NVMe over Fabric standard, and you don't need to install anything on the application server, which is great. But then you ask them, can you do network multipathing? And they say, sure, you just install our network multipathing driver on the application server, and you get network multipathing. So NVMe over Fabrics is not quite there yet, and of course we will adopt it if and when it will get there. One of the reasons we have an application side driver is exactly for these kinds of things. It's very hard to run high-speed networking without that entity, and certainly you cannot do network multipathing today without it. In a nutshell, the solution needs to be bulletproof. If I learned anything at IBM is there are no excuses. The storage customers do not measure reliability of a system 4 nines or 5 nines. They expect absolute uptime. Any kind of maintenance window is just unacceptable. So one of the key points to the E8 architecture and how we achieve it and how we actually unleash the bottleneck is a separation of control path from data path. Now, to some of you, that might sound trivial because networking and telephony protocols have done the separation of control path from data path back in the 80s. But it was never done for block storage before. And when we started dissecting block into this architecture, we literally had to go to the very basics. How do you achieve a read and write in this kind of topology and in this kind of architecture, claiming you separate control path from data path? There's no cookbook on how to do it. We've actually patented it. We've actually got the patent granted. And it's a very innovative approach. Each of the controllers needs to have enough information to be able to shoot IOs directly to the SSD that it wants to talk to. The controller, the box here, we call it a controller, but it is not involved in the data path. It is not invoked in the data path. It will not perform logical to physical translations like in any kind of quote-unquote normal storage product. So the AFA controller portion here, our agent service, needs to have enough of a brain to be able to map out user volumes into the SSDs that they get written on. So for that end, the control path talks to the metadata server and gets that kind of information. And I often get asked, so what gets implemented here and what gets implemented here? This is a trade-off that we have and the flexibility that we have. For every feature we design, we get to choose what gets implemented here and what gets implemented here. The design goal is that control path, namely complex logic, but simple computation and a low frequency event, gets done in the box. And it's done in a highly available way because we have two metadata servers here.
Okay, so as I write to the system, periodically the agent in my host machine is going to get allocated another block of flash from the MDS as I need it?
Or is it?
Yes,
No.
if you create a volume or you lose a disk, these are obviously control plane functions.
Oh, right, it's all thick provision, so it's, never mind.
So it doesn't have to go and look up anything on,
Maybe when they
on
go
the
through,
fly.
that'll be the case.
Now, the data path is the opposite. It's simple logic, but heavy computation and very high frequency. Every I/O is a data path activity. The design goal is not to have any of that run in the box because we then run into that very same bottleneck that afflicts all the all-flash arrays we're talking about. So the data path runs here on the application servers.
Like we said, you were saying that that's the part where your RAID calculations, all that has get handled in the controller on the host, flushed down to wherever.
Yes, I will show it in a second.
Okay.
Maybe even next slide.
Great.
So separating control path from data path is key to achieve the performance that we're getting and is key to unleash the bottleneck that we're targeting, and that's why we can get such high performance. So how do we do RAID 6 in a distributed fashion like that? Again, this is something we've patented and got the patent granted. The parity calculations, known as Reed-Solomon, we do on the agent service. And the host now needs to shoot N+2 IOs to N+2 SSDs. It needs to have enough information to be able to do that. There's no translation going on in the box. If there's translation going on in the box, we trigger a software entity in the box that needs to do per IO computation, and that will trash our performance back to square one. So you need to have enough of a brain here to be able to do that here. However, something like a rebuild is done by the controller. Why is that? Because it's a background activity, and we can time it. So the controller does not become a choke point. And we don't need to load the agents with unnecessary activity that will take down their performance. In fact, our agents on the servers only deal with the IOs that they themselves initiate. This is very different from a hyperconverged architecture where the software, the storage software you run on the servers, it takes care of the IOs that that server initiates, but it also fields and proxies IOs for the other servers, which I've always felt is an unfair thing. The tax that we put on the customer servers is directly proportional to the level of effort they employ towards E8. And there is absolutely no east-west communication in E8. The customer servers don't know of each other's existence. They don't communicate with each other. They don't care if they're there or not. They don't care if their networking between them is there or not. The only communication in E8 is north-south. All this entity cares about is being able to talk to the SSDs and to the metadata server, which all reside in the same box.
Outside of the box, it's almost shared nothing.
Yeah.
Outside of the aluminum that houses the SSDs.
So
from a data path.
Okay, so I'll get to that in a second. We support shared writable LUNs. It's flexible. It's malleable almost. If you take a box of E8 with, say, 100 terabyte and carve it out into 100 terabyte LUNs, 100 1 terabyte LUN, and dish out 1 terabyte LUN to each server, it is shared nothing. But if you carve out one huge 100 terabyte LUN and now share it between 100 servers, it is actually shared everything.
Yeah.
So E8 addresses both scenarios, and we support shared writable LUN which is very useful for clustered applications.
If you're doing shared writable run, I guess the servers have to talk to each other for reservations and stuff.
Never. They only talk to the box. They don't know of the others. That's why it's so scalable.
There has to be a distributed file system above it to arbitrate who writes where, when. But that's no different than if it was just,
No, I know.
lot.
But then they're talking outside of they're still talking to each other just at a higher level.
yeah.
The biggest problem with RAID 6, and this is true for any RAID 6 implementation, is what happens when the guy performing the write happens to die in the middle of the write operation. So unlike a simple write to a single SSD or hard drive, when you write RAID 6, you have a stripe. So you have, let's say, 4 plus 2 or 8 plus 2 or 16 plus 2. That's a whole bunch of IOs going to different destinations. Each such destination may respond or not at a slightly different time. During that time window, the writer might die. That is known in the industry as the write hole problem. And it's true for any kind of RAID 5 or RAID 6 implementation. It is even true for RAID 10. When you have 2 copies, the writer might die without knowing if the 2 copies have been updated. Solving that is very difficult. And solving that in our array is what I'm going to show you right now. And the way we do that is with a 2-staged write. So the host, first of all, writes to the RAM inside the box. And only after everything resides inside the box does it kick it to get flushed into the SSDs. And that protects us from both the host dying during the write or the controller dying during the write. If any of those things happen, all the data is still there to be able to retransmit the write and not get into the write hole problem.
Well, you're still exposed if the controller dies after the host gave it the final commit, but it hasn't made it to the SSDs. But that puts you in the same position as every other RAID array ever.
No, we're not, because we have this guy here. So they protect each other. They're one happy family. So even if it got...
I can kill them both simultaneously.
If you want to do that, we have high availability. So we have 2 MDS servers.
But like I said, that just puts you into and the same as every other RAID
Exactly.
array ever.
Yeah, we're as good as any other guy, but it's very difficult to do in a distributed fashion. And another nice thing we get from writing to RAM is a latency improvement, because the host can already give ACK back to the application once it's safe in RAM. The size of the RAM, at minimum, we need 4 gigabytes. Presently, we put 64 gigabyte or 128 or something like that. So we have a pretty decent burst buffer that we can use. And it's very useful for us. The battery backup unit protects us, so we can flush that dirty data to a safe repository upon power loss.
Thank you very much for calling it a burst buffer.
Yes.
So the 4 gig minimum is just to contain writes, but anything larger than that becomes a burst buffer.
So I guess during the demo, when you're showing like all those different IOPS at 10 million, and you guys were talking about 400 microseconds, chances are that if you're writing to that's because you've gone beyond, with the number of IOPS you're pushing, probably gone beyond your RAM buffer, right? And you're starting to, now you don't block, right? You go like SSD.
You're asking why does latency hike up as you push more IOPS?
Well, I guess I'm just asking what happens when you come up to, let's say you only have 4 gig, and you start writing beyond RAM, what your RAM can handle before you evacuate. Or do you block, or do you go right to SSD?
So it's funny, because SSDs intrinsically, they do the very same thing.
I'm sorry.
The SSDs have an internal RAM, and they buffer writes, and they flush them to NAND at their own disposition. That's why they have a super cap to protect that RAM. So even without our dirty RAM, you get pretty good performance from the SSDs. So we need it mostly for the RAID 6, and it does give some sort of performance benefit, especially if an SSD is getting confused by some sort of background operation, our RAM will be protective of it. So we're less less susceptible to SSD's latency spikes because of that. We have IOPS to latency curves. A lot of people ask us, so 10 million IOPS or latency, it only starts to make sense when you see the IOPS to latency curve. The more IOPS you drive to the system, and it's true for any system, the higher the latency, the average latency becomes. And we pretty much reflect what the underlying SSDs give to us. That's the thing that we use. We are seeing better numbers with Optane, but the numbers are pretty astonishing even with NAND, right? When we do 10 million IOPS, the average latency of the 10 million IOPS will be higher than if we do 1 million IOPS. So I think we have a slide about that somewhere here. I can show it. You can see where to position yourselves on the latency to IOPS chart. Finally, how do we achieve shared volumes with RAID 6? And this is also an answer to the question on why E8 requires NVMe drives. So there's two sides to the coin. E8 is an architecture designed to leverage NVMe drives, but at the same time, it is an architecture that depends and requires NVMe drives. Why is that? SAS drives have 2 queues, and you typically connect them to dual controllers. NVMe drives can have up to 64 queues. And what we do... 64,000 queues. And what we do is we connect each queue to each host. That allows multiple servers to write to the same NVMe drive without the need for arbitration. If that did not exist, the box would need to process the data path. It would need to wake up for each I/O and determine there's many writers or readers, and now I arbitrate and mux it towards the SSD. That's what a SAS dual controller does. NVMe drives have many queues, so they don't need to be capped at a dual controller. So all the servers in the network can read and write from the same SSD without conflict.
So do you give blocks of queues to the servers depending on how many hosts you have running?
We map a queue from each SSD to each host that needs access to it. And each host has got its private queue.
That goes to one core to the driver, right? So one core.
Okay.
Yeah.
Yes. So you can see here that the data path goes to 2 distinct queues in the memory that might go to the same SSD. At the same time, we achieve shared LUNs by the control path talking to an MDS that coordinates access. So in a shared writable LUN, there's no escaping it. When you do RAID 6 writes on the shared writable LUNs, you must serialize writes to the same chunk or stripe. It's a mathematical inevitability. This entity serializes it. So you could create a scenario where 100 servers are trying to write to the same LBA and say, oh, wow, your performance is limited there because we serialize. We're still going to probably have much crazily higher performance than any other storage product out there. But that's not really, that's kind of a pathological case. In reality, a shared LUN is used in carving it up into regions, the different nodes in the cluster axis. And in that case, there is no conflict. But now you see why NVMe drives are a key component to E8. And it also answers the question, why now? When we started E8, at least for me, there was a bit of a challenge to be able to say, how come in 2014, we're coming up with a new storage architecture? Why didn't anybody do it before? Because it makes so much sense. Everybody in networking and telephony did it years ago. The answer is that in SAS and SATA and hard drives in general, there's no need for it. The performance of hard drives is so low that there's no such challenge that you need to solve. It's only NVMe that brings this challenge to light. And it's only with NVMe that you can perform this kind of sharing without the dual controllers. NVMe SSDs started coming out at the very end of 2014. When E8 was founded. So you couldn't have done that before. That's the answer to why now.
As Intel puts up CPUs with a lot more cores, and they're coming out with numbers in the future that are going to be very high, is your agent going to have the ability to have multiple instances of your agent to serve maybe different partitions of servers like that have, say, 8 cores each that are running so they get their own paths and their own queues?
So already today, you can run the agent with as many cores as you want to assign to it. So if you assign 1 core to it, you get certain performance level. If you assign 8 cores to it, you'll get 8 times the performance. It is horizontally scalable.
And it's 1 queue per core. Is that how
Yes,
you get it? For that
1
and so you'll assign a queue per core.
Exactly.
Okay.
Okay.
There's your.
Yep, exactly.
So we see a difference between demo environments where we try to have as little gear as possible. So we load up the host with as many cores running E8 as possible. Versus actual deployments where we see 1 or 2 cores dedicated to E8 that usually takes care of any kind of performance need they have, and they can scale it out to hundreds of servers. And the impact, the footprint we take on the customer server is 1 or 2 cores. Today, servers are typically 20 to 30 cores.
Yeah.
Well, it's predictable. If I run this at full out, I know I will use these 2 cores at 100%.
Yes, it is capped to the cores that you provided it.
So yeah.
Okay, so Julie hinted at it at her presentation. How do you scale capacity? There's 2 different ways to do it. Each one has its own benefits and use cases. The simpler way to do it is what's known as federation. You bought 1 box, now buy another box. Since the controllers know where the SSDs are, they can talk to as many boxes as you buy. You can buy 10 boxes and have the controllers talk to them. In this case, each controller, each box is its own RAID domain and has got its own metadata servers. This is a classic case of federation. One of the benefits of this is that you don't need to worry about what kind of SSD capacity or SSD type you're putting in any box. So this box could be RAID 5 NAND, and this box could be RAID 6 Optane, whatever. A RAID group must be uniform in performance characteristics and capacity, but when you federate boxes, you don't really care. The E8 agent does something like an LVM concatenation of volumes if you want to get larger than a single box volume. And this is very useful if you want to add future capacity. Today you're buying a system maybe with 3.2 tera drives or maybe with 6.4 tera drives. In 2 years from now, you're going to buy a system with, God knows what they're going to have then, maybe 20 tera drives. So they cannot be part of the same RAID group.
Would it allow migration from box to box?
You can do it today with
I guess you could just
LVM.
move, probably, yeah.
You can do it today with LVM. The other approach we have is scaling to multiple enclosures which are clustered together. In that case, the RAID 6 or the RAID group can span or stretch between boxes. That mandates that the SSDs have the same performance characteristics and the same capacity. And this is useful when the initial deployment is large. So if we go to a customer and our largest box today based on 6.4 tera drives is 170 terabyte, and they want twice as much, we can give them 2 systems and they will view it as a 340 terabyte system. Of course, by mid next year, our numbers will double because the SSDs are constantly growing in size. One of the nice things about the 8 is it actually allows growing SSDs in size without worrying about them failing and creating a large blast radius. So the SSD vendors keep announcing a 32 terabyte SSD, 128 terabyte SSD. There's really no limit to it. There's enough space in the 2.5-inch SSD to put as much NAND as you want, but that's a huge blast radius. By putting high availability and RAID 6 on it, you can really use as large SSDs as you want. So in this case, you're creating a cluster out of several boxes. As Julie showed in her slide, the biggest we've tested is 4 boxes, which is pretty expensive setup, but it's just a testing limitation. There's no real reason why you couldn't do more. The RAID can be shared between boxes or striped between boxes. And interestingly, there's only 2 MDSs serving the entire cluster. Now, one of the reasons it's so easy for us to do that is because for the agents, the software entities running on application servers, the SSDs they talk to are merely network addresses. They don't care that one SSD is here and one SSD is there. Why would they care? It's going through the network to them anyway. So you can even, in theory, stripe it on many, many different boxes, each one having one SSD. It's not something we're particularly shooting for, but it's really a logical network path to find the SSD that it wants to talk to.